Okay, let's formally get started with today's session, week number 5, DSC707 Deep Learning. And just to give you a quick revisit that we started convolutional neural networks, so image recognition in the previous week, right? I'll just give you a quick recap of what we were looking at so that you can link the discussion that we'll do today with what we were doing previously. Okay. So we actually started our discussion with the basic operation, which is called convolution, right? So in convolution, if you remember, we have an image and then we have a small matrix, which is a filter, a small matrix, maybe 3 cross 3 or 5 cross 5. And we superimpose this matrix on top of the image, and then we take a dot product, right? So this actually is called convolution. We slide this small filter or window or kernel, whatever you want to call it, over the complete image, right, from left to right and top to bottom, and then we have an output, right? So this is how we apply convolution. Then we saw how convolution acts as a feature extractor, right? And if you remember, we had seen example of an edge detector. We started a discussion with a vertical edge detector that, okay, you can perform convolution and you can detect vertical edges. Then we extended the same discussion to horizontal edges, right? That by changing the values in the filter, we can actually detect horizontal edges. And then we said that, okay, instead of we deciding what feature to extract, why not let the model choose itself, right? So this was a whole you can say important idea that when you are using deep learning, you rather than fixing the values in this small filter, you let the model learn these values through backpropagation, right? As we'll see today in more detail. This was the main difference, that rather than some expert telling you that, okay, use this filter maybe for detection of edges, right? You just take these values as parameters, right? So all of these are actually parameters, and you learn the values of these filters through backpropagation, right? We'll see more on that today. And then we had seen some variants of standard convolution, that is strided convolution and padded convolution. In padded convolution, whatever input you have, you actually pad the borders so that you do not lose information at the boundary of the input volume. And similarly, strided convolution is that when you are performing convolution, instead of taking a step of 1, you can take a jump of more than 1, say 2 or 3 or whatever the value of stride is, right? So these are again hyperparameters that you decide prior to performing convolution, right? Then we extended the idea of convolution to volumes, right? That instead of performing convolution on a two-dimensional matrix, maybe an M cross N matrix, you say there's a third dimension. For example, if we are dealing with colored images, then the third dimension is actually the depth, which is the number of channels, right? So you have 3 matrices, one for R, one for green, the third one for blue. So actually, once you do convolution or volume, so if your filter is 3 cross 3, so since you have 3 channels in the depth, you will also have a third dimension in the filter. And we discussed that both of these should actually match, right? Again, we'll see more details on that in today's session. Then after all this information, we were able to produce a single layer convnet, right? That by combining all these pieces of information, how you can make a single layer of a CNN. Then we had seen a concept of pooling, where we downsample our input volume in terms of spatial dimension, right? And we saw that the intuition behind pooling and why is it needed, and a special type of pooling which is commonly used is the max pooling, where for a small region you just keep the maximum response and you discard the other values. And the last thing we had seen towards the end of the lecture was that we designed a small toy convnet to solve the character recognition problem, right? So since this is important, so I will again flash the small CNN that we had designed, right? That we have to solve a character recognition problem. So there are 26 characters, assuming we are talking about A to Z only in capital letters, right? So the last layer you have 26 neurons, and then the input image is actually a volume of 32 cross 32 cross 3, because we assume that we are dealing with colored images, right? So then we discussed that, okay, you choose some number of filters, size of filters tried, and then you go from one volume to another, right? So we had done in detail how you can add layers and how you can compute the size of the output volume if you know the hyperparameters, right? Again, we'll see more examples of this today. And then eventually, once you are done with convolution, you can flatten your volume and you can have fully connected layers just like you have in a traditional multi-layer perceptron, right? And this was an encapsulated way of representing ConvNet, right? You write like con, which is referring to a convolutional layer, then a pooling layer, then again a combination of convolution and pooling layer, two fully connected layers, and finally a softmax layer, right? And we had also calculated the number of parameters in each layer, right? And we had made some observations that normally the activation size goes down gradually. The pooling layers will not have any parameters because there's nothing to learn. And most of the parameters of a CNN, they actually reside in the fully connected layer, right? The convolutional layers, they have very few, relatively fewer parameters as compared to the fully connected layers, right? Okay, so now we'll be looking at a different perspective, that how we can fit all these pieces of information and specifically convolution in a network, right? So it will be the same discussion, more or less, which you have already seen, but this time we'll look at it from the perspective of a network, right? Rather than starting from the convolution, which we did in the previous week, right? So from the perspective of a network, you see, we talk about layers and we can discriminate between certain types of layers. There are, of course, many other, but what we are discussing here is a CNN in its very simple form, right? As we progress our discussions, we'll try to add more sophisticated layers to this CNN, right? But for the time being, we are only looking at the key ingredients or the key layers which you will find in every CNN, right? So of course there would be an input layer, right? There is no processing involved in an input. You just feed the data, and then the most important part is the convolutional layer. Then you have the activation function, and as we discussed previously, the most common activation function for CNN is ReLU. We'll see it in detail. And then you already know pooling layer, we'll just revisit it. And finally, we'll have the fully connected layer. So if we see a typical architecture of a CNN, right? So there's a very famous diagram that you will find in almost every book or every presentation, right? Which actually summarizes all the key layers that a CNN typically has, right? So you will perform convolution, and then typically you will have an activation function, right? So you will have convolution followed by activation function. You can replicate it as many times as you like. And then in between you have these pooling layers, which will actually downsample your spatial dimensions, as we had seen using max pooling, right? And you can repeat this combination multiple times, right? If you're designing a network, and eventually you have fully connected layers, and the final layer will have as many neurons as the number of classes, which we already know. Okay, so again, looking at convolution from the perspective of a network, right? So on the left, you see an image. The image is 32 cross 32. So we say that the width and height is 32 cross 32. It's a colored image, so the depth is 3. So the 3 you see here is because you have 3 matrices, each of size 32 cross 32, right? So that's why we represent it like a volume, which is 32 cross 32 cross 3, where the last dimension is actually the depth, right? And we discussed last time that you can choose any filter size. Typical filter sizes are always odd numbers, and most common choices are 3 by 3, 5 by 5, 7 by 7. So when we are choosing a filter size, in most cases in the literature, you will only see a filter size like 5 cross 5, right? It is understood, or it is implicit, that the third dimension of this filter is equal to the depth of the input, right? So that's why mostly you will not see this third dimension explicitly mentioned in a filter size, but you must know that even if it is not mentioned, it is same as whatever is the depth of the input volume, right? So in this case, we have an input of 32 cross 32 cross 3 and a filter of 5 cross 5 cross 3. So now what we do is, when we do convolution, so you see the filter is 5 cross 5 cross 3, which is like 75 values, right? So actually you are multiplying the values in the filter with the values in the image, or the pixel values in this region, okay? Because this filter is covering 5 by 5 region in the image, right? So you are actually taking a dot product of 75 values, which is actually, if W, they represent the values in the filter, so you are actually taking the dot product with the X, which is actually the input, or in this case, your input is actually the pixel values in the image, right? So you see it's more or less the same thing that you were doing in a conventional MLP. You take a dot product of weights with input, right? The only difference is that here the weights are actually the values of the filter. And then you will add a bias like we always do, right? So you see it's very much similar to what we have been doing previously. Now to show you a numerical example, right, which will give you some more elaboration on how actually convolution is done. So suppose we have this input image, which is like 5 cross 5 cross 3, right? Or maybe we paired it, right? So we have a border around this image, right? And we have two filters, right? So the filter is 3 cross 3 cross 3, and there are two such filters. Okay. So this one, which you see here, maybe this is filter 1, let's call it F1, and this one is filter 2, let's call it F2. Okay. So once you apply the filter F1 on the image, right? So what you do is, since you have three channels, so you superimpose this part on the first channel, you superimpose the second part on this second channel, and the third part on the third channel. So in every case, you have 9 multiplications in each channel. So there are total 27 multiplications, right? You add all of them together, you get one single number, right? This is very important. Of course, the result of these three convolutions would be like three numbers, A, B, and C. But eventually you have to add them so that you get one single number, D. Okay. So it means that you are taking a dot product of 27 values and you are adding them together. And then you add the bias, whatever the bias is, the single value you get is actually your output, right? Which, for example, in this case is 0, which we write in the output matrix. Then you can move your filter depending on the stride, it is 1 or 2, whatever it is, and you repeat this process. So you compute the second value of the output. You keep on doing it, and once you reach the end of the image, so that actually completes your output of filter 1. So this is actually the output by filter 1, or you can say this is the feature map or activation map when you apply filter 1, right? Because we already know that one filter corresponds to one feature. Now what you will do, you will apply the second filter on the complete image, and again you will have the second output. So this is the output of F2. So what you have, since you had two filters, so this is the output of one filter. So with two filters, your output is 3 cross 3 cross 2. So instead of two filters, if we were using 20 filters, then our output would have been 3 cross 3 cross 20, right? So as we discussed in the previous week, the depth of the output is always equal to the number of filters, right? So now just to, I'll now show you few visual illustrations just to better convey how convolution is applied, right? So you have three channels. You are taking a dot product on every channel. And once you have the output, you actually add them together, right? So eventually you have, you can say, one single matrix, a two-dimensional matrix for one filter. So one filter is giving you one matrix. K filters will be giving you K matrices, which you can stack together and represent as a volume, right? So another, you can say, illustration on how convolution is applied. Again, the emphasis is that when you are doing convolution across depth, right? So you eventually add all the outputs of all the channels to get one single number, right? This is very important, and I'm repeating it again and again because when there's some assessment like a quiz or an exam, so I give matrices and I ask student to apply convolution. So this is a very common mistake that they would do, that they will keep the output of every channel separate, right? Which is not true. So the output of one convolution is a single number because you have to add the 27 multiplications or the 75 multiplications, depending upon what the size of the filter is, right? So when we, why do we call it a layer, right? Because you see, you can, I'll come back to that in a while. But you see, when we apply one specific filter, for example, this given filter here, so it actually corresponds to a feature map. And what do we mean by feature map? That suppose this particular filter is detecting vertical edges. So all the points in your image where there exists a vertical edge, you will have a high response, right? So this would be an indication that that particular feature is present in these locations in the image, right? Now, this is a very important slide, right? So I'll spend some time on this again, because we want to discuss that why we are calling it, how we are linking convolution with a neuron, right? So you can think of you can say, you can think of this cell, which I have highlighted as a neuron, right? So this is actually, when you are doing convolution with a 5x5 filter, so you can think that, okay, this neuron is connected to this 5x5 region, right? And the weights of the filter are actually, or the values in the filter are actually weights on these links, W1 up to say W25. Okay, so you see, when you see it from the perspective of a neuron, if W1 to W25 are the weights on these edges, and whatever input you have is X, so what you do here, you actually multiply weights, okay, and then you add bias. So now you see, here again you are doing the same thing which you do in a conventional neural network. The only thing is that now we are looking at it from the perspective of a convolution operation. Now, once you have applied convolution here, what will you do? You will move your filter one position to the right. Okay, so maybe your filter would be like this. Okay, this one which I have highlighted with these bars. Okay, so you can think that this second neuron is actually connected to this part of the image, right? And similarly, your third neuron is connected to the part of image by sliding the window one position to the right. And similarly, you can say that, okay, my this last neuron, maybe this is connected to this part of the region, right? So actually, when you are talking about one filter, okay, it is learning one specific feature. So a very important difference with respect to multi-layer perceptron is that here the weights of all these connections will be same. Why they will be same? I'll explain in the subsequent slides as well. This is very important. You see, because suppose you are trying to learn an edge detector, right? Your weights are actually trying to learn how to compute a vertical edge, right? So what will happen is that when you are applying a filter, you are applying the same filter on every position of the image, right? It is not like that in the start of the image you are looking for maybe a horizontal edge, here you are looking for a vertical edge, and here you are looking for a curve. If you are searching for a feature, if you are searching for a horizontal edge, then you are searching for that feature in whole of the image. So all of these neurons, they actually have the same weights if you are talking about one single filter. So I understand it's a bit tricky, so I'll try to explain it further. Now just look at this, okay? We have a filter of 4x4, right? So you see, when we are applying the filter, the first filter, which we are calling W1, okay? So suppose W1 is a horizontal edge detector. So in all the regions of the image, we want to detect the same feature, okay? So it means when you see this layer of neurons, all the connections, they have exactly the same weight, which is a common property, which I'll explain later, which is called weight sharing. And this is a very key property of convolutional neural networks, which you won't find in a multi-layer perceptron, that weights are actually values of filter. If I have one filter, the same filter is applied throughout the image. So that's why in all regions of the image, my neurons will be sharing weights. They will have exactly the same weights for one filter. Of course, if I have second filter, then that filter will have different values, because there I am trying to learn something different. Okay, so let me explain the same concept, that why we call it weight sharing. I'll first explain this one and then the top one. So you see, as I told you, that the same filter is applied to all positions in the image, right? So when you are talking of this first neuron or second neuron or third neuron, if this filter is trying to detect this curve, right? So in all the positions, you are looking for the same feature. So all the neurons will have same weights. Okay. Similarly, there would be a second filter, say W2 or F2, right, which is trying to detect maybe a curve like this. So again, if it's a 3 by 3 filter, you will have 27 values, which will be shared across all regions in the image. And another component which is important with CNN is called local connectivity. Now, what is that? If you remember multi-layer perceptron, everything in previous layer is connected to everything in the next layer, right? Which actually results in a very huge number of connections. And when you have huge number of connections, it actually means that you are having a huge number of parameters. So in this case, if you see this neuron, okay, so you see it is only connected to this part of the image. Okay. Similarly, this neuron would be connected to some other part, and what would be the size of that part? The size of that part is same as the size of the filter. If it's a 5 by 5 filter, so every neuron is actually looking at 5 by 5 region, and that region is called the receptive field of a neuron, right? So what is receptive field? Receptive field is basically the part of image on which you are applying convolution, and the size is actually the same as the size of the filter. If you see it from the perspective of a neuron, so you can actually say that a neuron is not connected to all the pixels in the image. It is only connected to those pixels which fall in the receptive field, or in other words, it is connected only to those pixels on which you are currently applying convolution. Okay, now for the next 10 minutes, we'll not be looking at some new concept. We'll just try to reinforce and reassess that whatever we have seen so far, we have good, you can say, command on that, right? So I'll give you certain scenarios, and then I'll let you think that what should be the output, what should be the number of features, and so on, right? So let's see this example where we have, you can say, an image and a filter, right? Since we are not doing any padding, so when we apply this filter, the output we get is 28 cross 28 cross 1. Why 1? Because we are applying one single filter, right? Now, if we apply a second filter, then we'll get a second output. And instead of calling it output, few fancy names, as I told you earlier, you can call them activation map, or you can call them feature map. And why we have this terminology? Because if your filter is searching for a specific feature, then for example, if this is looking for a feature like this, so it will have high response in those areas where the feature is present, right? And it will have a low response in the areas where the feature is not present, right? So maybe this will better illustrate the idea that since we are using, suppose we are using two different filters, so every filter is actually learning a different feature, right? So maybe with this pink one is learning some other feature, this green one is learning some other feature. So eventually you will have multiple features, multiple filters will be detecting multiple features, you will stack them together and get the output, right? Now, if you see it from the perspective of a neuron, right? So you see, this actually is the equation which we used in an MLP. And in the present discussion as well, we are actually doing the same thing, right? You are multiplying weights with input, you are adding bias. And we'll apply activation function, though we have not discussed it as yet. But this part is actually what you are doing in convolution. You are 75 numbers, taking a dot product, adding a bias, right? So from the perspective of a network, nothing has changed, right? It's more or less the same idea, right? And the third dimension, which is new in comparison to MLP, is this dimension. And this is why, because we have 1, 2, 3, 4, 5 different filters. So that's why we see 5 here, right? So this is just the number of filters. So another visual illustration that suppose we don't do any padding, we apply 6 filters. So we get, you can say, an output which has a depth of 6. Now, some discussion from the perspective of, you can say, understanding that you see, we have only seen application of convolution on the first layer, on the image directly, right? So you know very well that each of these features is like a feature extraction, which we have discussed many times, right? But now, when you have the second convolutional layer, so this actually volume will be an input to the next layer. right? So when you are talking about the second convolutional layer, the output of the first convolution is actually input of the second convolution, right? So it means that what you are feeding as input are actually activation maps where certain features have been detected. And now you are applying convolution on that, you can say, feature map. So the second convolutional layers will actually combine those small pieces of information into relatively high level features, which will subsequently be fed to the third convolutional layer. So now you see, as you are going deeper, you are learning more high level features, starting with very basic features at the first layer, right? So now, if you remember in the first session, we discussed hierarchy of features. So now it will make more sense that why we use this term hierarchy of features, because the output of one layer is actually serving as the input of the next layer. So as you go deeper, you actually start learning more and more high level feature, and maybe by the end of the network you have some filters which detect handwriting or a face or maybe certain object, a chair or a table, right? Because by that time you have many layers of convolution which are learning high level data specific feature, right? And just to again visually or intuitively tell you how convolution actually works. So suppose this is an input image, right? This is a back of a car, right? And these are our 32 filters, right? So these are just visualization of filter, right? We have a 5 by 5 filter, we have some values, and we just visualize them as an image, right? So you see, for example, just focus on this filter, right? So what is this filter? There's some like orange sort of thing in between, right? So when you apply this filter, so it will give you high response in those areas where you see something which is similar to this feature, right? So now you see this output, that in this image you have this orange light here. Okay, and when you apply this filter, which is actually trying to detect a feature like this, so you see in this region you have a high response, which I was telling you earlier, but now you can visually see it, that since in the image we found this feature, so this white color is actually high response and the darker color is actually low response. So when you see this white color here, it is actually telling you that this particular feature is detected in this part of the image, right? Which can be a useful information. And as we discussed a little while back, that since you have a series of convolutional layer, so in the initial layer, the filters are like this, where they are detecting very low level features. And as you go deeper, you actually apply convolution on the output of previous layer. So you learn more and more high level features, right? So this was something about convolution. Let me just also tell you the next, you can say, concept, which is actually not a separate layer. You can call it a layer, or you can actually have activation within the same layer. It's only depends how you see it, right? So you see previously in case of MLP, common activation functions were sigmoid or 10H, right? But CNN, right? It's common that people would be using this ReLU activation function, right? Because it is easier to train a deep network if you are using this activation function. So what is ReLU? We discussed informally. But today we'll be discussing this activation function formally. So if you see a plot of this function, it tells you the story that if you have negative values, right, you make them zero. Right? So all the negative values will become zero. And this is a line at 45 degrees, right, which means that uh, if the value is positive, you just keep that value. So in other words, if I apply ReLU on -2, since it's a negative number, output is zero. If I apply ReLU on -10, output is zero. If I apply ReLU on, say, a positive number 4, the output is same number, right? So this is how ReLU works. So after convolutional layer, it is common that you apply this activation function, and eventually you will have only positive values preserved, and all the negative values they are actually suppressed to zero, right? Okay, so as we discussed earlier, a complete you can say CNN is a sequence of convolutional layers followed by activation function, right? So for example, this is the first layer of convolution, which is mapping a volume from 32 cross 32 cross 3 to 28 cross 28 cross 6, because we have applied 6 filter, right? So just think for a moment, what should be the filter size for the next layer, right? So maybe the spatial dimensions you can choose. Say I say, okay, filter would be 5 cross 5. But now you must know that your filter must actually be 5 cross 5 cross 6. Why? Because the depth of input is 6. So when next you will perform convolution, you can choose any spatial dimension. For example, these two could easily be 3 cross 3. There's no problem with that. It's your choice. But here you don't have choice. This number has to be 6 because the depth of input volume is 6. Right? So if we apply 10 such filters, right, without padding, so this volume is mapped to a volume of 24 cross 24 cross 10, right? You can do it directly, or in the beginning you can always use this formula, which was like n minus f plus 2p over s plus 1, right? You can, if you cannot do directly in the beginning, you can use this formula. N is the input, f is the filter size, p is padding, s is stride, and then you add 1, right? So since we are not doing any padding, so that's why 28 is actually, uh, you can say 28 minus 5 is 23, and stride is 1, then you add 1, so you get 24, right? So this is how we are getting 24. Okay, again, just to stress on the point, there was also a question by one of your colleagues that you see, we have seen a numerical example where depth was 3, but depth would be 3 only in the first layer. In the next layers, depth could be anything, right? Depth could be 100. So for example, suppose this is the third layer of a CNN. So this is your depth. Suppose it is 100. So it means this is your one filter of 3 by 3. So the depth of the filter is also 100, means this is also 100. Okay. And now when you will apply convolution, so you see what will happen. This first channel, it will be multiplied by these 9 values. Similarly, this second channel, it will be multiplied by these 9 values. The third one with this one, and similarly the last one with the last channel. So eventually all of these are added, which are like 9 plus 9 plus 9. How many multiplications? 100 times. You add all of these values. This is not the number, this is number of multiplication. 9 multiplications plus 9 multiplication 100 times, and then you will get this single value. Okay, one value, and then you will move the filter one position to the right. Okay, so it's easy to understand from 3 inputs where the depth is 3, but the same concept is applicable when you have a depth which is more than 3. It could be anything, 100, 200, depends on what the size of the volume is, right? Okay, so again, uh, just a recall from the previous lecture that when we are dealing with layers, there are 3 important parameters: depth, which actually corresponds to number of filters; stride, that how long a jump you take when you are doing convolution; and padding, that how much you want to pad the borders of, or if you don't want to pad at all, right? So previously, we have already seen this general expression to compute the size of output volume, right? But we had seen it assuming a square image of size n cross n, right? Which is okay. In most cases, you will be feeding a square image to the CNN, but this is not always necessary, right? You can have an image where you can have dimensions like you have different width and height. It is not necessarily a square image, right? And it will have certain depth, which can be any number, 3 for colored image, 1 for grayscale image, and it could be anything for the subsequent layers, right? So the hyperparameters that we use in every layer is, first is the number of filters, the size of the filter, 3 by 3, 5 by 5, 7 by 7, stride, and p, right? So this input volume will map to this output volume where you can compute it. It is exactly the same formula. Instead of n, we are using w and h. That's the only difference, right? So you see, previously it was n, now I'm writing w1 minus f plus 2p, right, divided by s plus 1, which is exactly the same formula. We just have a different variable for width and height rather than keeping it the same. And the depth of the output volume, depth of output is equal to the number of filters. If you remember, k was the number of filters, right? So this is easy. Another important thing is that how do we compute number of parameters in each layer? Okay, so we did it numerically, but if we want to generalize, so you see number of parameter, they are actually the values of the filter. Okay, so when you are using a 3 by 3 by 3 filter, how many values you have in the filter? 27. So it means there are 27 parameters and plus one bias for this filter. If you are using 10 such filters, then you multiply it by 10. So your total number of parameters is like 280. Okay, if we want to generalize, so you see what is the number of parameters in every filter? It is F cross depth of the filter, right? And what you do, you have one bias. Okay, so this is the number of parameters in one filter. If you have k such filters, you multiply it by k. Okay, so this is the generalized expression that if someone asks you to actually tell the number of parameters in a layer, we did it numerically last time, but now this is a generalized expression. You can simply plug in values of f, d, and k, and you can find the total number of parameters for a given layer, right? So just for, before we do a break, just for practice purposes, I'll show you the answer, but just think over it that I'll show you some examples and ask you what should be the output, what is the number of parameters. So in this first example, we say, okay, our input is 32 cross 32 cross 3. There are 10 filters and each filter is 5 cross 5. Stride is 1, padding is 2. So what would be the size of the output volume, right? You just think over it for a moment. Just think of an answer and then I share with you. Okay, so since we are doing padding, so you can guess the spatial dimensions are preserved. So the output is 32 cross 32 and the depth would be same as the number of filters, right? So this should be your output volume. If you cannot compute it directly, you can plug in values in the formula and you can compute through formula as well. Okay, so we were doing an example where we were trying to compute the size of the output volume, right? So as we discussed, you can do it directly or you can use the formula, whatever you feel easier, right? So the next related thing that we must know how to compute is the number of parameters in this layer, okay? And what are number of parameters? They are actually the values in the filter. So as I told you, what is the filter size here? Filter size is 5 cross 5, but actually it is 5 cross 5 cross 3, right? So these are the values in one filter, okay? And then for every filter you have a bias. And how many such filters do we have? We have 10 such filters. So it is 10, so it is like 75 plus 1 into 10, which gives you 760, right? So the total number of parameters in this layer is 760, right? So again, easy way, you just find out how many parameters are there in a single filter, and then you multiply that number by the total number of filters, which was 10 in this particular example, okay? Now one more example, suppose you have an input of 56 cross 56 cross 64, okay? And we are doing convolution with 1 by 1 filter, okay? So now this 1 by 1 filter may sound strange to you, but we'll see in detail. There's a very famous architecture which is called GoogleNet, which uses this 1 by 1 convolution. So why we actually use it, that we'll discuss later. But for the time being, you can just treat it as a numerical problem, that just for getting why we are doing 1 by 1 convolution, you have the information that the filter size is 1 by 1 and there are 32 such filter. So what would be the size of output volume, right? So you see, since we are assuming that in this case, whether you won't be needing any padding because the filter size is 1 cross 1. So if you use a stride of 1, the output would be 56 cross 56 because you don't lose anything in the spatial dimension, and the depth of the output would be same as depth of this as the number of filter. So it would be 56 cross 32, right? And if someone asks you what is the number of you can say parameters in this layer, so one filter is 1 cross 64, right? Plus one bias. How many filters are there in total? 32. So this would be the total number of parameters in this layer. Okay, so now we have seen plenty of examples of convolutional layer. Now let's revisit pooling layer, which in fact we have discussed in detail in the previous lecture, but just a quick recap that pooling is actually a downsampling layer, where the objective is to reduce the spatial dimension, right? And when we say spatial dimension, we mean width and height, right? We are not talking about depth here. So basically, this is a visual illustration of what we mean by downsampling. So if you have, say, a volume of 224 by 224 by 64, when you do pooling with the common settings where you take a stride of 2 and a window of 2, so the spatial dimensions are reduced by a factor of 2, right, from our previous discussion. So it will become 112 cross 112. But you see, the depth has not changed because you apply this downsampling to each channel separately. So you are actually spatially reducing the dimension, but the depth would stay the same, right? And the reason is that we want to have fewer number of values when we go to the fully connected layer. So that's why as we go deeper in the network, it is common that we shrink the spatial dimensions, right? So as we discussed earlier that today almost all the networks use max pooling, but previously there were networks which use sum or average as well. But these days you will rarely find a network which is not using max pooling, right? And if you want to find out the size of the output volume after pooling, then it is exactly the same expression which we used for convolution. The only difference is that you don't have any padding term in this, because in pooling we don't do any padding. Similarly, pooling does not change the depth, so that's why you see that the depth of output is same as depth of input. Otherwise, both of these are the same which we were using for convolution. And the most common setting is this one, where you use a window size of 2 by 2 and a stride of 2, which will reduce your spatial dimension by a factor of 2, right? So every time you actually shrink by a factor of 2 your spatial dimension, right? Of course, you can use other settings, but this is the most common setting that you will find in most of the networks, right? Okay, so after pooling layer, next we have fully connected layers, which is exactly the same idea as you have already seen in a multi-layer perceptron, that every neuron in previous layer is connected to every other neuron in the next layer, right? So you can have one or more fully connected layers after the convolutional layers, and the last fully connected layer will have number of neurons which is equal to the number of classes, right? So for example, if we are solving a digit recognition problem, so we'll have 10 classes, softmax activation function, and it's just like you have been doing with the traditional ANN, right? Okay, now when we talk of training a CNN, so you see, initially we don't know what are the filter values, right? Maybe we can choose the number of filter, which is a hyperparameter. We can choose the size of the filter, but what are the values in those filter? Whether you want to detect horizontal edges or vertical edges or both or something else, right? So the weights of the filters are actually learned through back propagation, right? Because you have seen previously that numerically we are actually doing exactly the same thing which we are doing in a MLP. So you can just randomly initialize the filter values or the weights, and then you can run back propagation. So with different iterations, it will be your network will learn to find good filters or features which will help it in solving the classification problem, right? So from an intuitive perspective, you see training a CNN is just like training the human brain, right? Because when when we are born, we have a mind which is fresh. There nothing is learned. So with time, when we see different examples, we start to recognize them when we see a test case, right? And the same is the case with CNN, that by looking at the data and the labels of the class, it actually tries to, or it learns with different iterations of training. It learns that what are the good features that I should extract so that I can discriminate between the classes under study, right? Okay, now this is an important slide. You see, when we train this, you have an end-to-end system where you have input and you have output, right? So in between, you have convolution, pooling, activation function, fully connected layer, everything going on. So it is like a box where you have different connections, and here you have the loss function, you back propagate it, you learn the weight, right? But logically, you can identify two different logical groups within this black box, right? So you see this part of the network, which is actually doing convolutions, okay? So convolution we know is an operation which extracts feature. And since we are repeatedly applying convolution and the output of one layer becomes the input of the next layer. So all this part where you are applying convolution, this is normally called the feature extractor part of the network, right? That because this is the part which is learning filters, which is learning features. And if you see this later part of the network, which is like a conventional MLP. So this is actually your classifier part, right? So if you see them as two independent logical groups within this end-to-end model, so you can say, okay, the convolutional part is extracting actually features, and then those features which are extracted by the convolutional part, they are fed to a classifier, which is like an MLP, fully connected layer, right? Which is learning those features and which is performing classification, right? So please do remember this discrimination, because in some of the discussion that we'll do shortly, we'll revisit this these two separate entities. Although it's one single model, but we can discriminate between these two parts. One is doing feature extraction and the other is doing classification. Okay, so before we conclude this particular discussion and move on, I'll just give you, as always, a quick walkthrough of how you can implement a very simple CNN without, you can say, some fancy layer, just very basic layers, right? So you see operations that we do are convolution, activation function, pooling, fully connected layer, and softmax, right? So these are the typical, you can say, operations that we do. So now how do we implement it? It's fairly simple. For every layer, you will have one single, maximum two statements in TensorFlow that will help you implement the network, right? So as always, just like you have done with MLP, we create a model, right? Now we have a sequential model, so we'll keep on adding layers using the add function, right? So now if you want to add convolution, right? So it is you will create the layer conv 2D. There is also something called con 1D and con 3D, right? But we are not talking about that for the time being. Since we are using two-dimensional convolution, your filter has basically you are applying it to the image, and the third dimension is split, is implicit. So you will be using two-dimensional convolution, right? This 3 by 3 is the size of the filter, right? And this 32 is actually number of filters. Okay, so basically there are 32 filters, each of size 3 cross 3, and of course the third dimension is implicit. Then this is the activation function. Padding same means you have to do padding. If you don't want to do padding, you can write valid here, and you can give a name to every layer. It's not mandatory, but just so that you can refer to it. So we are calling it con1. And since this is the first layer, we also need to tell the input size. So the input size is 150, 153, means it's a square image of size 150 cross 150 cross 3. Why 3? Because we are dealing with colored image, right? Then after convolution, since we have added activation function here, if you don't want, you can add activation as a separate layer, right? But normally we don't do it. After the convolution, as an argument, we also tell the activation function, but there's also a possibility that you can add activation function as a separate layer, right? Which normally we don't do. Okay, then you have pooling, right? So since we are doing max pooling 2D, and again, this 2 by 2 means you are using a window size of 2 cross 2, right? Then again, you have a convolutional layer, then pooling, convolution. So you see, you are repeating. So this part till here is actually your feature extractor, right? You can repeat this sequence as many times as you like. And then once you are done, you flatten. If you remember, flatten converts a volume into a vector, right? So if you have a volume like this, since you are going to fully connected layers, so maybe you want to represent it as a vector, means one-dimensional representation, right? We have not seen yet, so I'll just skip this. We'll see it in a while. So just forget about this. And you see the next you have these layers. So this part you have already implemented in an MLP. Dense is a fully connected layer. So we have 512 neurons, then 128 neurons. And finally, since maybe we are solving a two-class problem, so we only have one single neuron in the output layer, and basically the sigmoid activation function, right? So this is one, you can say, very basic implementation of a CNN. Then you can load data, call the model.fit function, just like we were doing in a conventional MLP. and then you can train your model, right? So this is some detail of the layers which I already discussed with you. So with that, we come to the end of this part of CNN, right? So if there are any points that are required to be discussed, we can do that.